Welcome back, everyone, to the next talk. Uh, the speaker of our presentation is Sarika Bhattacharya from CSIR. She is going to talk about role of interaction potential in correlation between structure and dynamics.
So first, I would like to thank Ranjini and Mahesh for organizing this amazing school and inviting me to give a talk here. So um, just now, if any one of you saw the previous title, then the material of the talk is going to remain the same. So I'm going to talk about role of interaction potential and correlation between structure and dynamics using a softness parameter. A large part of the introduction of the talk has been given in the given by Andrea in the morning, but I would still do. Okay, can't change slides. So basically, we are talking about systems which are in the supercooled liquid domain. Now, what do we mean by supercooled liquids? Liquids, when they are cooled beyond the melting temperature, cooled fast enough, they enter a supercooled liquid domain. And the temperature at which they enter the supercooled liquid domain is called the onset temperature. And there are multiple transition temperatures in supercooled liquid. I'm not going to go into the details of that. Now, why do we call it supercooled and not just a liquid, but still call it a liquid, is something I'm going to talk about a little now, and then show how we can use liquid state theories to understand these systems. Now, what happens is while the system enters the supercooled liquid domain, the viscosity or the relaxation time grows very fast. This is the angel plot again, what you have seen in the morning today. Some of them grow Arrheniusly. I haven't yet been able to stop using the word Arrhenius, but I'm going to do that soon. And some of them grow in a much faster than Arrhenius growth, and that's basically your activation energy shows a far stronger temperature dependence. So here the activation energy is constant. That's the reason you have this e to the power like exponential e by t, whereas here the e itself is changing. Now this is for a large number of systems. This is something very common and seen. Now, what also happens, those were the macroscopic things. What happens at a microscopic level is that the dynamics becomes intermittent. It is no more a continuous dynamics. Particles move intermittently. They are caged and then they break the cage, move. So it's an intermittent dynamics where there's a decoupling between the short and the long time dynamics. And that gives rise to the relaxation time, like if I plot the overlap function or the density correlation function, that at high temperature it will follow an exponential behavior with a characteristic relaxation time. At low temperature it initially decays, which is within the cage, then there is a plateau, and then there is a decay from that plateau, and this plateau becomes longer and longer the longer these particles are within the cage. Now, while this dynamics is changing its characteristics, the way it moves, if I look at the structure, like if we look at the structure hardly shows any change. You know, one is at high temperature, one at low temperature. It looks very liquid-like. There is no effective change that any one of us can pick it up in our naked eye. So what it says is that, okay, there is a small change in structure but large change in dynamics, and this has a consequence, and which I'm going to explain soon. Now, when I talk about structure, how do we measure structure? There are multiple ways of measuring structure, but the very simple way of measuring structure is calculating the probability of finding a particle at a distance r. It's such a simple thing that, you know, it's too trivial, but this is also a very important quantity, the radial distribution function, because in liquids, if you know the radial distribution function, you can calculate the pressure, the energy, the compressibility. It also gives you a potential of mean force, the effective force between particles, and it also can be plugged into theories like mode coupling theory and dynamical density functional theory, and can give you the dynamics. So in the heart of the liquid state theory, this very simple quantity is present, and it is a very powerful but simple function. For solids also, if you know the GR, you can actually predict the mechanical and magnetic properties and other things. Now, what happens in the supercooled liquid domain? Like, you know, here it's by changing of density, the structure has been plotted from this paper. You can hardly see any change. If it was not shifted like that, there was no change. Could almost hardly any change would have happened. But at the same time, while the structure was changing so little, the dynamics changed over 7 orders of magnitude. Now, this clearly tells us that probably the structure plays no role in the dynamics in the supercooled liquid domain. That's what it is. And then this is something again Andrea mentioned in the morning, but I'm going to tell you again, is that two systems with different interaction potential, one with attractive Lennard-Jones potential, other with a repulsive counterpart of it called Weeks-Chandler-Anderson potential, gives very similar structure. And this comes from van der Waals' idea, who thought that structure is formed by only the repulsive part of the potential. The attractive part only creates a background. Now, this was a success for them, that you can use repulsive potential to predict structures. So whereas the structure hardly at high or low temperature shows any change, the dynamics at high temperature of these two systems are similar, but at low temperature they become order of magnitude apart. Now this again kind of made the community think that structure has no role to play in the dynamics, and any theory, that's what these two people said in a series of 4 papers, is that any theory which uses structure to predict the difference in the dynamics will fail. So that was the conclusion. And then there is one more thing which is interesting, and which Rajesh also mentioned, is that there is a heterogeneity in the dynamics which is not there in the liquid domain. So you find some particles which are fast, some particles which are slow, and these regions are which are fast or slow, they grow in size. So they are called cooperatively rearranging regions, and then they grow in size. And the question we will ask is, what gives rise to this dynamic heterogeneity? So then, if I kind of put together some of the features of the supercooled liquid, I will say that, okay, the viscosity or the relaxation time grows faster than Arrhenius. There is a decoupling between short and long time dynamics. There is a marginal change in structure with large change in dynamics. The dynamics becomes heterogeneous, and then there are these patches, which is called cooperatively rearranging regions. Now, the first question is, what gives rise to the heterogeneity? Now, usually, if supercooled liquids at low temperature, or like at very low temperature when they undergo glass transition, behaves like solids. Now, in solids, it is known that if there is a dislocation in region, then that's where the mobility is maximum. So then that's the first thing people started looking at, that to look for defects in supercooled liquids. And as you can see, looking for defects here is kind of quite a challenge. So then the question is that, what is an order parameter which can describe if there is an heterogeneity in the structure, then what is the order parameter which can describe the heterogeneity in the structure? That's kind of the search. And then one of the pioneering work in this search was done by Peter Harwell, who showed that low frequency vibrational modes are some modes which kind of like regions where the particles are mobile are also connected to low frequency vibrational mode. Now, this is something which comes from taking the Hessian, calculating the vibrational mode. You can't really connect it to directly the structure, although effectively there should be some effect of the structure. After this work, there has been a large number of studies, and mm, this paper actually puts together some 18 order parameters and explains that some of them perform well, some of them do not perform well. And the one which came out there as one of the winner is the machine learning study, which Andrea spoke to you today morning. So what they do is they describe a softness which is a weighting the radial distribution function, and that is what describes the particles, like the order parameter in that case. And without going into the details, because I wasn't aware that she's going to speak about this today morning, so I kept a little bit of slide to give an example of what it does. It's kind of a classification problem. It's a supervised learning, teaching the system that if you have a fast dynamics, what would be how your environment around you will look, and if you have a slow dynamics, how it will look. And in this way, they kind of classified the fast and the slow particles, and then with an unknown particle, they tried to look at the environment and predict if it's a fast or a slow particle. And it is quite successful, as you could see in the morning, that they applied it to many systems. And also, they applied it to this problem. This problem is extremely important because this is one of the system where the structure is very similar, but the dynamics is very different. So anytime anyone tries to see if any structural order parameter works, this is the test system to look at, these like actually looking at these two systems. So what they had shown is that the softness parameter of these two systems are different, and this difference in the softness parameter can explain the difference in the relaxation time. Now, what any machine learning study can do is it can make amazing prediction, but some microscopic details are missing there. So you have a weight function, but you do not know where this weight function, why certain parts of the GR is weighted higher than some other part of GR. So if we can have a microscopic theory, that would be the best way to look at it. And so there is a need for a microscopic theoretical approach to describe the structural order parameter, which depends on the pair structure, which is basically the GR or the Fourier transform of it, which is the SQ, the structure factor, which is measured in experiments also. So what Andrea mentioned today morning is why this GR or the structure factor becomes attractive is because it is also measured in experiment. So that's the reason, if we can predict something, then it can be applied in experiments too. Now, here comes a molecular mean field theory, which we had developed earlier. Chandan is also a co-author of this paper. So if you want to understand the variation of density of one particle, you can write it in a Fokker-Planck equation. And here you will find that to understand the time dependence of one particle, you need to know the way the other particles around it behave as a function of time. And this is a well-known BBGKY hierarchy in liquid state, like in theory. And so the dimensional reduction that machine learning does is a similar thing what we do here by applying a mean field approximation. What we consider is, we don't consider the background to be mobile, and we say it's a frozen background. And in that frozen background, we want to see how a tagged particle will move and feel caged. Now, to understand what would be the effect, so you can write it in terms of a potential, where the potential can be written as a functional derivative of the free energy functional. And it's a well-known free energy functional, Ramakrishna Yusuf free energy functional, where it tells that density at two positions interact via a direct correlation function. A direct correlation function is an effective interaction between two particles. It's not the actual interaction. Now, if you use that, and then the expression of the potential, which we call a caging potential, can be written in terms of direct correlation function and the structure factor, which is the Fourier transform of GR, and the direct correlation function itself can be obtained from the structure factor. So that means in this expression, if I know the structure factor, I can actually predict the caging potential of the particle. Now, if we do that, we find that as a function of temperature, so there should be a beta here. We scale the potential by beta, and that beta phi r goes to deeper and deeper potential as we go to lower and lower temperature. Now, we were actually, so it started, we had developed this theory for something else. And then the softness paper came out looking at WCLJ potential, and we were actually influenced by the softness parameter described in machine learning. And he said, okay, we can actually look at the curvature of the potential here and call it a softness, because that's basically the spring constant, which would be kind of the softness of the potential. So we can kind of calculated the curvature of the potentials there. And for a multiple, we did it for a large number of systems at different densities. There are active systems here too. We kind of plotted the softness against temperature, and we saw it's always following a linear behavior. So then when we tried to fit the relaxation time against the softness parameter, we found that it is not showing, for certain systems it's showing an overlap, but in general there is a spread there. So which means that if we know the softness, we do not know the relaxation, like we can't predict them in an absolute term. We need to know something more. And Yes. Those are the densities. So we took the WCA potential at different densities. We took the Lanajon's potential at different densities. The fragility changes actually when you change the density. Oh, so we don't change the softness. We at every density we look at the structure factor, and from the structure factor, using that beta phi r expression with the structure factor, we can calculate the potential. And then we look at the softness of the potential, and at every density you can vary the temperature and look at how the softness would change with temperature. Okay, so now when we did for a larger number of systems, this is not going to work, then we do not see a collapse, data collapse, and then we said, okay, let's look what's happening. This is not an angel plot exactly, but this tells you that the relaxation time of these systems vary differently with temperature, which means I have different, they are, some of them are strong, some of them are fragile, which means that, like, you know, this delta E has a very different temperature dependence for these systems. Now, earlier I showed you that the softness and the and the temperature, it varies inversely with temperature. So we said, okay, let's try to plot the activation energy, which is obtained from the relaxation time as a function of inverse softness, and we could fit them to all of them to linear behavior. Now, if I write an expression down from here, I would say that the activation energy is some constant plus B prime by softness. Now, which means that the temperature dependence of activation energy comes from the temperature dependence of this structural order parameter, how it changes, but also the B prime plays a role here, that, you know, if B prime is strong, that means that there is a stronger coupling between the temperature dependence of the structural order parameter and the temperature dependence of delta E. Whereas for actually for active strong systems, we found B prime is closely, like, it's grazing here. That means B prime is 0, and it is independent of the temperature dependence of softness here. So when we put them together, we find that the relaxation time of a system can be written in this way in terms of the softness parameter, and now we can get a data collapse with system dependent parameters. And it tells us that the activation energy, like how the relaxation time will change with temperature, will depend on the temperature dependence of softness, and also how this parameter B prime, which actually tells me how the dynamics is coupled to the softness parameter, how strong that is. If there's a strong coupling, then S will contribute to the temperature dependence of relaxation time. If it's a weak coupling, then S will not contribute to the temperature dependence of the relaxation time. Now, this was done at a macroscopic level. However, yes. Hmm. Oh, okay. Uh, So delta, these are all scaled by tau alpha. So we do not go below the tau naught, which is which is basically the high temperature relaxation time.
The second figure.
Yeah. So you can see there is a tau naught sitting here in describing delta E. Okay, so the relaxation time is scaled by tau naught. So it's going to be like when tau alpha becomes tau naught, delta E is going to be 0.
And but that their S will not be like not infinity, right? I mean, there will be some critical value. Is it, or
No, I did not follow. Tell me.
so if 1
what,
over S,
huh.
so if S becomes infinity, then it will be
No,
the
it is
origin.
not. No. S doesn't change like that with temperature. So it doesn't become infinity. So do you see the S variation with temperature?
What's out?
The plot there.
Okay.
These are S variation. They are finite values.
Okay.
Even at 0 temperature.
Okay.
Okay. So there is nothing which changes with S. It is basically tau becomes tau naught, tau alpha becomes tau naught, and that's where your delta E, according to this expression, would put us. That's the way the fitting has been done. Okay. So now it is well known that so what we were looking at, we were trying to look at dynamic heterogeneity. Yes.
I have a question. So after introducing that softness parameter, when you try to link that the relaxation time did not fall on, for all the systems did not fall on that. So you defined another parameter B that refers to the strong or weak coupling of all the systems.
Yes.
So I mean, does that not like that varies for every system
Yeah.
according to you? So to make a connection between structure and dynamics, is not it like a bit confusing to define a parameter that does that? Because B that you introduce here, it varies for all the systems, and you have defined that.
Yeah, it came out from my fitting actually, and then I realized that okay, there is a parameter B. So what I'm going to show at the end of the talk is that the softness can vary, or the structural order parameter can vary in the system, but how strongly your dynamics is going to be controlled by the structural order parameter will depend on this parameter B. So it's not like for every system you will see the same structural variation giving rise to the same variation in the relaxation time.
Okay,
There
but
is a structure
yeah,
dynamics correlation, but it is system dependent.
okay, okay,
So all systems will have structure dynamics correlation, and this will be depend on how strongly the structure will contribute to the dynamics will depend on the parameter B. And that will come up as a theme of my, like I'll be, once I go through another few slides, I'll be able to tell you that more.
okay, okay. Thank you.
So now the whole idea is we started with,
To clarify that structure dynamics uh, relation is different for WCA and the Leonard Jones.
yes, that's what we find actually. They're not going to be same. So I'm going to show that at the end. So and yes. So I don't have the plots here, but initially we did not look anything above onset, but recently we have done calculation above onset because Tanaka shows Arrhenius behavior above onset, and we do see the similar thing. You know, if we calculate the tau versus the softness above onset, it is linear, and then it starts going away from Arrhenius behavior below onset. I can show you the plot actually later on. But initially, we had never looked at it above onset, and there is a reason for that. We don't believe that this theory should be valid above onset. Yeah, so strong systems will not have this issue, probably. Yeah. So now what I started with is trying to understand the heterogeneity in the dynamics, and that's the whole reason I had created a structural order parameter. But what I've shown till now is something which is a overall behavior, an average quantity that I have calculated. So then I have to now use this theoretical formulation, which is developed for liquid state theory, to do something which is at a per particle level. And this is kind of a challenge, and we were not sure it's going to work or not to begin with. So what we do here is, this is the expression, okay? And I realized that to do a structure calculation per particle level is horrendous. It's so much of fluctuation, I cannot do anything with that. But what we realized was that this depth of this potential is inversely proportional to softness, and it can be worked out like if you have a harmonic well, then if you take the double derivative and the depth of the potential, they get correlated inversely. So what I realized is all I need is the depth of the potential and not the whole functional form of the potential. So then the depth of the potential can be now, with a Fourier, like if I do a Fourier transform, it can be now written in terms of radial distribution function and direct correlation function in R plane. So what this tells you is all I care about is the probability of finding a particle around me and how I'm going to correlate what is my interaction with the particle. That's what is the direct correlation function. So this functional form, this one, I can now actually calculate at a particle level by using this approximation that the GR for a particle would, if I, what I'm going to look at is I'm going to look at probability of finding particles around me. So they will be kind of straight, fixed positions where there are particles there. So what we do is we kind of add a Gaussian to it around that position and smoothen the GR. And the width of the Gaussian will make it like, depending on the width of the Gaussian, the smoothness of the GR will change. So we do that, and we do see an effect of the smoothening also, how it affects it, and we kind of take a value of this delta at 0.09, sometimes 0.06, and they work quite well. So the first thing what we see is that yes, we use it with a, oh, I missed that line here. We use a hyperneted chain approximation which connects it to GR. So basically, if I know the GR, I will be able to calculate everything in the softness parameter. So now, first thing what I do is we calculate the probability distribution as a function of temperature, and we can see a heterogeneity there. That's the reason there's a probability distribution of the softness which changes with temperature. And here is a heat map to show you that yes, the softness can be localized at different regions, and there can be hard and soft regions in your system. Now, I talked about a softness parameter, but the softness parameter can have an effect in the dynamics only when it has enough lifetime. If it changes immediately, then I will not have that, there won't be any effect of it on the dynamics. So what we look at is we look at the time, the lifetime of the softness parameter, and the solid line is the lifetime of the softness parameter. The dashed line is the lifetime of an like basically it's an overlap function. And what we find is the softness parameter and the overlap function has a very similar lifetime. So which means the softness parameter is a good can be a good quantity to predict my dynamics. What we look at also is something which I don't think Andrea presented it today, but they had also worked in their paper, is we take some particles which are not moving, look at the softness, take the hardest particles, and then try to see, even when they're not moving, how their softness can change while the other particles are moving around it. This is kind of gives rise to a facilitation, and we see that eventually it moves, it changes. So while this calculation is going on, it is all done on particles which has not moved within that time scale that the calculation has been done. Also, different values of softness shows a variation and kind of matches, like comes to an average value of softness. And this is something very similar to what has been obtained in the machine learning studies. If you can see how similar the expressions, how similar the figures are. So then we can say that the softness evolves with time, even though the particle, so if a particle moves, definitely the softness of the particle will change because the local environment changes. But even when the particle doesn't move, because of the mobility of the other particles, this environment can change, and that is what we show here. So here is a heat map of the softness, and here are some mobile regions. We can see a correlation between them. Now, what we did here is we know that the GR of particles which are soft will be less defined, GR of particles which are hard would be more defined. But what we did was we took a fast and a slow particle and looked at its GR, and we find that yes, the fast particles have a less structured environment, whereas a slow particle has a more structured environment. We did not have to do much search to look at a fast and slow particle and look at the difference in GR. When we do an average difference in GR of the fast and slow particles, we can see that the peak and the crest and the tape is where the maximum difference comes up. So there is a difference in the structure of a mobile and an immobile particle. Now here is a quantity which Andrea has already presented, but I'm going to tell you again what it is. We calculate the fraction, we take all the particles with certain value of softness. Then in that we calculate the particles which are mobile within that time range, that delta t that we use to calculate this parameter. And then we call them fast particles, and that fraction is plotted here. As we can see that at high temperature, the softness does not change this fraction of particles which are mobile. But as we come to lower and lower temperature, the softness starts or rather the fraction of particles which are going to move starts depending more on the softness parameter. So at high temperature, there is hardly any coupling between the structural order parameter and the dynamics. But at low, it comes up. And this is something very similar to what again has been obtained in machine learning studies. And the reason for it, we believe, is that at lower temperature, cages are longer lived. And because of that, the structure around the cage will be able to contribute to the dynamics more than they will contribute at high. When I say high temperature, I'm still below the onset. Below the onset, I'm at a high or a low temperature. Now, this is again another plot you have seen in the morning, that if we now plot this probability distribution as a function of inverse temperature, we can, at different values of softness, we see that they behave like, they have an Arrhenius behavior, and then they all fall in a straight line. And you can actually calculate an activation energy from this. So now, this is again something which has been seen in machine learning studies. Now, where these lines cut is the predicted onset temperature. And Andrea had given you a mathematical expression of what that value should be. I am going to present you a more physical, intuitive argument about why that is going to be the onset temperature. So if I follow a curve, then what it shows me is that particles which are having low values of softness beyond this point will have a higher probability to be mobile, which is completely a breakdown of the theory. So then why does the theory break down? Is basically, in this whole argument, I had considered a frozen background. And I can only talk about a cage when there is a short time and a long time, there is a decoupling in the dynamics. So this decoupling in the dynamics can happen only below onset. Above onset, there is no difference between a short time and long time dynamics, so there is no well-defined cage, and we do not believe that any, like our theory which talks about a caging potential, will be valid above onset. So the onset there is basically predicting that above which the prediction of the theory will not work. Now, I come to the problem of trying to understand how the WC and LJ potential, like how the softness parameter can predict the dynamics in the WC and LJ potential, where the GR is very similar, but the dynamics is very different. Now here, I have plotted it in a different scale. I plot, and it is plotted against 1 by beta phi r, but it's the same as the softness. So I'm going to, like, you can consider it as a softness parameter. So what we find is that as we go to lower temperature, we find that the tail, which is basically the softer particles over here, they start moving inwards. And they don't seem to be any different in the LJ and the WCA potential. They look very similar, the way it behaves as a function of temperature. If I also plot the probability of the fast particles to move, there also it appears that everything is very similar for the WC and LJ potential. They behave quite in a similar manner. Then I use this Arrhenius behavior and try to predict the onset temperature. And the onset temperature also both behave in an Arrhenius manner, and the onset temperatures are predicted quite well in these two systems. So which tells me that from this analysis, the softness parameter is a good predictor of the dynamics, and it can predict onset, it can tell me that the dynamics the softness will determine when the particle will move, and everything seems to be working quite well. However, when this is the difference in the dynamics of the two systems. When we calculate the average of the softness parameter, this is how so they appear to be different. Now, when I plot it against the dynamics, the plots come closer, but if I calculate the activation energy, I do see the slopes are different. This is my B prime parameter, which is going to show me that the activation energies and slopes are different. Now, which tells me that there is a system dependence between the correlation of the dynamics and the structural order parameter, and that comes up in the slope. Now, I take this. Wait, this backward, forward. Yeah. They will be quite different. That's the reason the fragility comes different. You cannot collapse them. There's no way a WC and an LJ potential relaxation time can be collapsed, because basically you can scale, like if you plot it against T by Tg, you will see that the rate at which they are growing are quite different. It's not like you can collapse these two plots. And you can bring them closer when you plot it against softness, because the softness parameters are different. If we compare, although I showed you that the probability distributions are same, but again we find something which machine learning also finds it, that the LJ particles are more harder, like the structure around the LJ particles are much more, like much harder than that around the WCA particles. So basically, that's the reason you see this softness parameter having a lower value for the LJ potential, and which tells you that there will be a change in the relaxation time, but it appears that there is still some system specificity there. Now, okay, so now what we do is we calculate the activation energy from these two systems, and we plot it against the inverse softness parameter, and we do see that there is a difference in the slope. And now we can always argue that this is something which is only our system. It depends on the order parameter that I use, and there must be some order parameter which will be able to take care of the difference between these two systems. But here I show that this is Andrea's paper with others, and here clearly they show that there is a difference in the activation energy of the LJ and WCA system. This is Hajime Tanaka's another order parameter, which they claim is a many-body order parameter. There they show that the tau alpha, when plotted against 1 by this order parameter, the slopes are different, and only with a parameter D2 they can collapse them on the same plot. So which clearly tells us that between these systems, the structure dynamics correlation is not the same. And I will come back to that point later, but let me tell you something else a little here. I now told you that there is a many-body correlation in supercooled liquid, whereas now I'm claiming again that I can calculate the two-body correlation and predict the dynamics. So how do I reconcile these two statements? So here, if the way we have done it is, okay, every particle has its own environment, and which is obtained from a two-body correlation, the GR. We can describe the caging potential there. But now, if I am caged, suppose I'm not caged and I'm allowed to move in the short time, but if the particles around me are caged, then I can only move this much. I won't be able to make a larger jump. So when I think about a long time correlation, my softness alone is not going to give me any understanding. It is only going to be a softness of larger number of particles around me. So it's a collective softness, which is a coarse-grained softness, which of course we use it with an exponential dependence, that the particles which are farther away will have a lower contribution to the central particle. Particles which are nearby will have a stronger contribution. So you kind of coarse grain the softness parameter of every particle, where for every particle this parameter is calculated at using the two-body information. So once we do the coarse graining, and then we try to correlate the dynamics with the structural order parameter, we see at short time, this L is the coarse graining length. At short time, the smaller values of L shows a larger contribution, and then it starts dropping. But as you go to longer times, the values of L, which are bigger, starts contributing more, and then there is a non-monotonic dependence. This is at a particular temperature where we find L equal to 4 is contributing most. It's probably the same L value that Andrea was mentioning in the morning, that 4 particles need to correlate together for a particle's mobility to be for the softness to be described. Now, the same thing when done for a WCA potential does not show as much growth in correlation as it shows in the LJ system. And also, what I'm going to show you in the next slide is the values of L where this peak happens, non-monotonic dependence also changes. So what we do now is we take a displacement in the long time and we start correlating it with the coarse-grained L, the coarse-grained softness. So coarse-graining length is given here. And what we find is at different temperatures, the peak comes at a different position, which tells me that when I'm at a high temperature, I'm not affected much by particles which are far away. But as I go to lower and lower temperature, particles which are further away starts contributing to my softness description and predicts my dynamics. So this L max grows with lowering of temperature, and it is higher for the LJ system at the same temperature and also at the same scaled temperature. And this kind of gives a static length scale, and we can actually calculate the softness parameter from this by doing this coarse graining, and it starts showing some kind of a length scale out. Now, what we also do is we take the peak values of this correlation and plot it against temperature. And you can again see that for the LJ system, it shows a stronger dependence with temperature compared to the WCS system. And this reminds us what this activation energy was also showing, that the activation energy of the LJ system was growing much strongly with temperature compared to the WCS system. Now, how do we understand this structure dynamics correlation was our point. We know that there appears, LJ system appears to have a stronger structure dynamics correlation. And to understand this, we kind of calculated something which is which we call the community inference. It was which is proposed by Koslovich, Parrott, Jack, and Koslovich in 2020. So what they do here is they try to look at the microscopic details of the structure, difference in structure in a system. So in that calculation, this is very similar to a mutual information theory calculation. You can break the system up into different communities, look at the difference in the structure of the community K with the average structure, and the wider the difference in the structure of these communities are, the higher will be the value of delta S2. That's what this prediction says. This is very similar to, as I told you, like calculation of mutual information. Now, we have a continuous distribution of our order parameter, but what we decided is we will take an average value, and from there particles which have higher value of softness, we will call them soft. Particles which are lower values of softness, we will call them hard, and break them up into two different communities and calculate this quantity, the delta S2. And then what we find is that delta S2 grows much strongly for the LJ system compared to WCS system. Now, this can be done for any order parameter. I can take the machine learning softness parameter, I can take vibrality, I can take Hajime Tanaka's many body order parameter, define the system into multiple communities and try to understand what is the difference in the structural parameter. So what this tells me is that in the LJ system, there appears to be a larger heterogeneity in the structural order. Like both have hard and soft particles, but the difference in structure of the hard and soft particles are wider in the LJ system compared to the WCS system. And this, according to Koslovich, can be used as a proxy of a structural fragility, which I'm not going to go into the details here. And this, for us, describes things quite well. So what we see is that sorry, this oh, this is terrible. Yeah. So this difference in the delta S2 is something mimicking my B prime parameter that I had initially talked about when I talked about structure dynamics correlation. So any system where there is a higher heterogeneity in the structure will probably have a stronger structure dynamics correlation. That's what it appears here. Now, what we also wanted to do is compare our order parameter with some other order parameters. And if I look at our order parameter, it is some kind of an effective caging potential, so which gives me a feel that it's kind of an energy. So the local energy is what would be another order parameter to look at. And along with that, what we looked at is also a two-body excess entropy, which is in the community does study this a lot. Now, what do we mean by excess entropy is that ideal gas entropy is the highest entropy of any system. Now, due to, in the liquid state theory, due to correlation between particles, the entropy reduces. So that's the reason the entropy comes with a negative sign. Now, this two-body excess entropy gives us the reduction of entropy due to two-body correlation, again the GR. So I've kind of confined everything to GR or calculating it at a particle level in a local thing. Now, what we find is, so here, of course, we have done a coarse graining. And what we realized when we coarse grain 1 by beta phi r versus when we coarse grain beta phi r, there is a difference. When I coarse grain 1 by beta phi r, I start getting dominated by particles which are in a less structured domain. When I coarse grain phi r, I get dominated by particles which are in a deeper potential, more structured environment. Now, what we find here is if we look at the time dependent correlation, then it looks like the phi r, the caging potential and the local energy kind of correlates well with the dynamics till a longer time in the LGS potential. Whereas when we go to the WCA potential, the the local energy has almost no correlation with the dynamics, whereas the entropy starts contributing more to the dynamics. So if you take a repulsive potential, we expect the entropy to contribute more to the dynamics because there is no attractive, like there's no enthalpic contribution. If we go to a attractive potential, we consider the enthalpy to contribute more. And it appears this structural order parameter that we have proposed can capture both the enthalpic and entropic contribution. So that means for a colloidal experiment or any other experiment where we do not know the interaction potential, we do not have to worry about it. And we can use the structural order parameter and it will pick up the contribution, be it enthalpic or entropic. So with that, I would just like to show you some, so this is an experimental system. I think Rati has already presented enough, but I'm going to just show you some of them. And here we can actually see in a crystal how the softness parameters change. Here it is a sheared system. The softness parameters were done at initial time and the particles which are mobile were put on that and they kind of collapse quite well. So which means the structural order parameter can predict the mobility field at a later time when you shear the system, and here it can predict the defect in the crystal, and of course it can predict things in glassy systems also. Now with that, I would come to summarizing my talk here. So what we gave you is a physical picture of a caging potential using only the pair structure or radial distribution function. What we find is that the LJ system, there is a higher correlation between dynamics and structural order parameter. And then LJ system shows a larger variation also in the structural heterogeneity. And in the LJ system, it appears that the dynamics is driven by enthalpy. For the WCA system, it appears to be driven by entropy. And the structural order parameter that we calculate can capture both the enthalpic and the entropic contribution. Now, before I end, I just thought I will just mention one thing that we have seen in polydisperse system. In polydisperse system, what we realized was that structural order parameter or any other order parameter was not a good predictor of the dynamics unless you take the size into consideration. So here is something like a multiple linear regression. What we have done is we have done a linear regression analysis by calculating them by treating this, putting in the information of the mobility and the structural order parameter and the size. And we have done it in terms of there is a vibrality parameter and the size. And then we calculated the predictive power of the system without, like for each variable. So there are 3 variables. We have combined them with size, each of these 2 variables, and have also calculated them independently. We see, and then what we do is once we train the system, like kind of create this, get the lambda 1, lambda 2 parameters, we take a new mobility and find out the difference between the predicted mobility and the actual mobility values, and these are the error bars plotted. What we find is that unless we put in the information of the size at higher polydispersity, none of the systems are good, none of the order parameters are a good predictor of the dynamics. So the size starts contributing a lot more to the dynamics is what we have seen here. With that, I would like to acknowledge people who had contributed to the work. The initial mean fill model was developed in collaboration with Chandan. The experimental work, which Rati has already presented, was done in collaboration with Vijay. My former postdoc Manoj here did the initial part of the work, developing the macroscopic theory. Mohit, my current student, developed the microscopic theory, and Rati, who is in the audience, did all the experimental work. With that, thank you for your attention.
It's really nice. Very, very, very beautiful work. Um, Recently, this is a paper with Sean Rideout and Indrajit, where we just posted it recently, where we just use a simple trap model, right? So we take energy barriers that come from softness, and we say there's some intrinsic distribution of energy barriers, and then we just use the trap model to describe things. And we found that we got these are systems that Indrajit analyzed the harmonic repulsive spheres where fragility changes a lot. And we found that actually we could capture the trend of fragility quite well with a simple model like that. But the magnitude was off. So the trend in fragility was right, but the amount of fragility was not right.
Okay.
Which seems to suggest that the facilitation that's in Sean's more fancy model that I talked about
Yes.
is really important. And so I'm wondering if you can sort of tease these things apart in your theory. How much comes from facilitation versus how much comes from just having a distribution of energy barriers, which is different for WCA and Leonard Jones.
Yes. So I haven't actually looked at facilitation, but we can always look at it by looking at least the softness evolution and see if the WCA and the LG system has different time scale of facilitation, which can be looked upon. But at least whatever we have seen till now shows that it's a wider variation of this softness parameter. I would say structure. I wouldn't say softness parameter, wider variation of the structure, which shows that thing. But yeah, that would be something interesting to look at if the softness evolution happens at a different time scale for a LG and the WCA system, and if there's the facilitation difference there. We can look at it. Thank you.
If there are no more questions, let's thank our speaker again.